Alright, hell yeah. So today we got linear algebra, and we're going to go over the proof of the LU factorization process. And now it might not be a full proof, but it's at least not just doing a bunch of hand waving. So I'm kind of excited about this video because it was kind of eye-opening to me. And so, and I had to Google some stuff, but let's begin. So hell yeah. So with LU factorization, we're going to have a matrix A. And what we want to do is have a vector of unknowns, and then we have a vector of constants. And so given any matrix A, we want to be able to, and given A and B, we want to solve for the unknowns. And this is very similar just to, matrices are set up with like one equation, like one equation, two unknowns. Two equations, two unknowns. If I have two equations, and then maybe they're xy equations, then this variable, will be a matrix xy. If it's three equations, three unknowns, it'll be xyz, and so forth. And so the solution, how do we get these answers xy? Well, we're going to take the inverse A on both sides. And now we just have inverse A and then the matrix of constants. And so now we just do a very simple multiplication of two matrices, which is very elemental, and we get our answers. And once we get this inverse of A, this is always going to be the inverse of A, and therefore we can throw in different values of B, and that's the reason why you would do this. If you only were just doing this one time, you wouldn't do this process. Forget about the inverse. Just solve it using a simpler process like Gaussian elimination. Okay, hell yeah. And so what LU substitution does is it says, hey, if this is matrix A, let's say matrix A is a lower and an upper. And so a lower, if this is a 2 by 2 and this is a 2 by 2, a lower is going to have values in the diagonal and the lower and 0 right there. The upper is going to have values in the diagonal and the upper and the zeros anywhere this side of that diagonal. Hell yeah. And when we get L and U and multiply them together in this order, because the direction matters. You can't do it in the reverse, but we'll get A. And then so why do we do that? Well, it's because we're going to have an equation that says the inverse of A is going to be, now this is key, parentheses have to go around this, and that's kind of your starter. If we said this is A, cool, these two things are identical. But now what is the inverse of L times U? And so there's a proposition that says we have to reverse the order or put the upper first, inverse of the upper, times the inverse of the lower. And that is going to be the inverse of A. And so that's going to be the process. Alright, hell yeah. And we'll see if I go over the proof at a later point in this video. And then I guess probably the last takeaway is the inverse of any matrix. I'm just going to say the inverse of matrix A is it's 1 divided by the determinant of A times the adjoint of A. And then the adjoint of A is just the cofactor transformed of A. And you get the cofactor by finding the minor and then determining if it has a sign change based on the location of where you took the minor. Anyway, so that's the general gist. But the juice of this video is, well, let's see where the juice is. Because to get an upper matrix, that's easy. We're going to have some sort of A. Let's say it's a 3 by 3. And all of them are values. So we have a value everywhere. And what we're trying to get is zeros in those 3 spots. If we got zeros in those 3 spots, we would have an upper matrix. And so we use this process of Gaussian elimination to hey, maybe get that to be 0 by doing something to the upper matrix. And this is where it was a turning point for me today. Because and what I should have done up here is how is this related to people that aren't doing matrix algebra on a daily, if I have like x plus 2y is equal to 3, and then negative x minus y is equal to 1, I can put this in matrix form. A is going to be the coefficients that are right here. So I see a 1, a 2, a negative 1, and a negative 1. So that is going to be my matrix of coefficients. My variables and unknowns, the vector of unknowns is going to be this. So matrix vector, so this is your matrix X, is equal to your matrix of constants. You know what I mean? Hey, this thing is equal to 3, this thing is equal to 1. So there's a lot of problems where there might be a difference between this structure and then these outputs, where if I change these outputs, you know what I mean, this structure doesn't really change. And so that's where if I can find the inverse of this. And then, so cool, so I went over that. Now I wanted to relate it to this, because if I'm trying to get this to be a 0, well, typically what we do is just be like, oh, look at this. I can just add these. So that's one thing. And then, you know what I mean? If I add these, then I get 0x plus y is equal to 4. Cool. Now what, though? You know what I mean? Is this a third equation? If this was equation 1, equation 2, and I even can't even, like, tell you 100%. Like, so we did something to both of these equations. Like, now what? I think, I'm just going to go out on a limb here, that I either get to use the new equation, but only one of the other ones. And I think that's true. But that's where, you know, especially when I'm doing the Gaussian elimination, I want to be at least, yes, that is a, you know, even me, like right now, I'm limited in like, well, I know I can't, there's not 3 equations, 3 like independent equations, we just have 2, and so we're going to say, hey, let's say it's the top one and then the new bottom one. Alright, hell yeah. And so let's go over maybe kind of one of these examples, because this is where even this textbook, I don't think they do a good job of showing you what these elementary processes are. And so that's the bulk of this video, but we kind of have to set up, you know, kind of the, like, what are we doing part. So if I have this matrix, and I want to get this 4 to be a 0, what they're gonna say, and I'm gonna actually write this out, because sometimes, you know, doing it on a fresh sheet of paper from scratch where you don't have, that's why textbooks are, there's a lot of information on here. So now here's our matrix A, and what I want to do is get this value to be 0. So what the textbook is gonna say is this is row 2, and I want to modify row 2. So after I do a process, the upper row is going to stay the same. Row 2 is going to change. Row 3 is going to stay the same. So hell yeah. And they're going to say row 2 is going to be this row 2 star, because now it's new. So the new row 2, and this is cool because they're going to say, they're going to do it one way where I don't think you should, the way that they're going to lay this next part out isn't even how you would lay it out if you did the elementary matrix. So that was just the mind blown part today. But anyway, so and so they're going to take the values in row 2. So we can start with the first one, 4. And then they're gonna subtract it. I'm gonna add the opposite. So we'll do what I would do first and then what they would do. So I'm gonna add the opposite. But you're gonna do this to you're going to multiply the upper by some sort of value. So if you did a subtraction, you would have to multiply the upper by 4. And that's what you would multiply that first row. It's way easier, I think, if you just say, hey, I'm going to multiply the first row by -4. And I'm going to add row 2 to -4 times row 1. Cool. So then when we do this, you know, this value right there becomes 4, that value in row 2, minus, so I'm going to do it this way. So 4 plus the multiple, and the multiple is -4. So that's the multiple that we're going to be doing with that row. So this value is 4 plus negative 4 times 1. And that's the new value right there. So this is 4 minus 4 is 0. So that's how we get this value to be 0. Now the next one is going to be 5 plus negative 4 times the value right there, 2. And so this is 5 minus 8. That's going to be negative 3. This one is going to be 6. That's the value in row 2. Plus negative 4 times that value in row 1. And so we have 6 minus 12. And that's going to be negative 6. Oh, and I forgot to put these right there. But hell yeah. So now we have a 0 there. And we made a modification to this second row based on multiplying this first row by something and then adding it. So we actually, we did a plethora of things. We multiplied the first row by something, and then we added that row to row 2. And then we did not change row 1. So all those things are going to be explained by this little e, the elementary processes. And I think it's not even going to look structurally like this. And once I explain it, it's going to be like, oh, hell yeah, let's do that every time. And this process is just hand-waved. I think, even in this textbook, it's not, they shouldn't do it. They should, if we're going to introduce elementary matrices, you should stop doing this process. You know what I mean? Because the process will look totally different. So yeah, so let's now we're going to go on a side tangent and explain at least what these two processes are, because this process switches rows, but when it comes to LU subfactorization, you're only using the first two processes. So that's kind of what it says. It says, for LU factorization, we do not allow the row operation of swapping rows. I mean, you probably could, but you would have to like undo, you know what I mean? I would have to figure that out, but obviously you're just trying to build an upper and a lower, trying to build it the simplest way possible. Okay, hell yeah. So now we're going to talk about what these elementary matrices do. Alright, booyah. And I think this is kind of the fun part because it was kind of the eye-opening part for me today. What an element, and then this is so wild. Because what we've been doing up to this point in this book is, well, I don't even know. Slow down. Anyway, so we're going to, yeah. So the elementary matrix operations are, what's this one? This one says that we multiplied row 1, and we're starting, and I think, you know what I mean, we're starting with a 2 by 2 identity matrix. Cool. How do you get this one? Well, I'm going to just multiply row 1 by 2. So I think that's probably the easiest thing and to see. But even this is just, I can't just, I can say so. This isn't how I would write it at all. And so I think that is what that was the eye-opening thing. Now this one, what did we do? Well, this one we actually multiplied, I think in this one, well, what are they trying to do? I think we multiplied row 2 by 2 and then added it to row 1. So hell yeah. So the two operations are that you can take a row and multiply it by something and be done. You know what I mean? And just be like, sweet. And then the other operation is you can multiply one row by something. And then, let me jump ahead. And then you're not going to change that row. But you are going to multiply this row. And then, like, cool, add it, or, subtract or add it. But you can add it to another. Let's just think about all adding. So I'm going to multiply this row by something and then add it to that row. That row is going to change, and I'm going to maintain this original, the structure of that row. So, yeah, that sounds like three things are going on. Okay, so the first part is, and the cool thing about this is you can use variables. So bummer. So, yeah, let's keep it crispy. So, so for this first one, and this brings up the kicker now, is because I'm going to take this inverse matrix and then I'm going to like augment it. So this has a structure of AX equals B. You know what I mean? I mean, this is essentially what any, like this A, multiplying A by a vector, this is a transformation. So this transforms the original vector that you're starting with. So you're saying that, hey, this is the vector that I'm starting with. I want to transform it. And what do I want it to look like? I want it to look like 2, 0, 0, 1. You know what I mean? And so we're multiplying matrices, so I can't just throw a 2 upstairs. You know what I mean? It probably there's going to be a 2 upstairs. You know what I mean? Then what does everything else look like? And so something even like this is like, well, all I have to do is just put A, B, C, D here, and then just solve for those. Because what we have is that when we multiply matrices, we have 2 rows. So you know what I mean? That's like 2 rows of equations, and here we have would you say this is, I don't even want to talk about, you know, I'm bad, if this has more than one column, I don't know how to explain it, but anyway, but let's just show what the matrix multiplication would do. It would say 1A, so the first one would be, yeah, and so if we do this, 1A plus 0B is equal to this value, you know what I mean? So that's how we do it. This value is this first row, first column. This one is in the second row, second column, so it's second row, second column. And we're going to get 4. So this process is going to get 4 equations because there's 4 values. The output is 4 values, so I'm going to get 4 equations. Alright, hell yeah. So for the first equation, it's 1A plus 0 times B is equal to 2. Hell yeah. The second one will be, let's get this one, it's 0A, 0 times A, plus 1 times B. Hell yeah. And I'm just putting these values up front even though those are in that side. But anyway, and that's going to be equal to 0. I mean, and we should be starting to solve this. If this is 0, hey, A is 2. All right, we're done. You know what I mean? We're done with that one. A is 2. Cool. And then this one is 0A plus 1B is equal to 0. Well, B has to be 0. Okay, hell yeah. So moving on to our other equations. This one is going to be second row, first column. So we have 1C plus 0D. So I have 1C plus 0D is equal to 0. So 1C is equal to 0, C is equal to 0. And then D, this value right there, or I mean the equation is solving for this value, so it's going to be second row, second column. Second row, second column, 0C plus 1D is equal to 1. Okay, so D is equal to 1. And now we know what this should look like. And so, hell yeah. And so A should be, we should have 2, B is 0, C is 0, and D is 1. So that is what it should look like, and that is the elementary operation. So what this says is if I, and this is almost like a, what do you call it? A tautology or, Oh, you know what? I'm so glad I'm doing this, though, because all the proofs require, you know, usually you're using some sort of, you're using the identity matrix for something. But we went through that whole process just to say that A times the identity matrix is B. Well, the identity matrix times any matrix is just itself. You know what I mean? When you multiply those two together. So this has to equal that, and that's what we found. So A, B, C, D has to equal that. And, yeah, but don't think of it that way. Because I was just like, well, that seems redundant. But nah, think of this is your vector. I mean, we're just starting with an identity vector, but we want to do something to it. And what do we want to do? What does this one do? This one just multiplies that top row by 2. And you couldn't do anything else. You couldn't say, oh, I'm going to multiply by the bottom row by 2 and then add it. Because look at the bottom row. It only influences that number. You know what I mean? So then if I added that up there, this number would be 2. This one wouldn't be changed. So this is why it's an elemental operation. There's no other way to change these diagonal values except by multiplying, something by that row. Or visually, that's what we see. I see, hey, in that row, we multiplied the entire row by 2. So that's visually what we're seeing. And so, yep, so hopefully that was a decent explanation. And so, yeah, so think of it as you're taking the identity matrix, and what we want to do is multiply that top row by 2. And so, yeah, so I think it is worthwhile to do the whole process, to be like, this is the matrix that I want to modify. I want the matrix to look like this, and that's the same thing as multiplying the entire top row by 2. This becomes 2. 0 times 2 is still 0. And then so what do we need to multiply out here? Because this is an augmentation of this matrix. Well, we have to multiply this matrix, and it's very useful to go through this process to see why these values are what they are. Because a matrix is just a series of equations, and we can see what those equations are, 4 equations, and we can see what the unknowns are. So I think it's very useful to do it that way, and then just be like at the end, be like, well, no, duh. Any matrix times an identity is just, the identity you can just throw it away. You know what I mean? It is. It's not that you just eliminate it, as if you do multiply A and the identity together, you'll get this. And we can say it's A prime. You know what I mean? These two multiplied together might be A prime, where A is equal to A prime. You got to be careful here because that looks like, could look like the inverse. But anyway, so you have, yeah, these two could be A star, and then A is equal to A star in this case. Hell yeah. All right, so now we have to see what's going on here. And, hell yeah. And this one doesn't look, it doesn't, I have to be like 2 steps ahead of the game to be like, oh yeah, no duh, you just multiplied the bottom row and then added it to the top. But in Gaussian elimination, that's exactly what we want to do. We want to, multiply one of the rows, and typically it's the other way around. That's why, maybe for this textbook they could also, it wouldn't matter if this was this way, it's still an elementary operation if the 2 was down there. And so in a second I'm going to show that what we just did was we had, here's our identity matrix. What's an elemental thing we can do to it? We can change the value on a diagonal. You know what I mean? So we could do that, or we could change that value. And how you change that value is because you multiplied by a row. You multiplied a row by some sort of multiple. That's what you did there. What we're going to show here is that we're going to have an identity matrix, and identity matrix, and what we're going to do is modify it. So so we're going to get a value there. And how do we get that value to change? Well, the only way to get that value to change, and it could be any number, is to multiply this row. So we have to multiply that row by something, and then add it to that row. So so row 2 gets multiplied, and then we add it to row 1. And I think it's almost, we're going to get into it, but it's also useful to say, well, we're going to add it to the multiple of 1. You know what I mean? 1 times row 1. So that's kind of also what we're going to see through that process. All right, let's try this one out. So we have some sort of matrix, A, B, C, D. This is what we're going to augment our identity matrix. And we want it to look like, the output is we want it to look like similarly to multiplying this by something and then adding it to the top row, but keeping the bottom row the same. So that is visually like what I'm wanting this to do. And so, and let's just run through, and so yeah, this is A, this is X, and this is B. Alright, so the 4 equations, if I'm going to solve for this one, first row, first column. So this is the matrix multiplication. A, so we have A times 1 plus B times 0. So now you can kind of see I'm doing it a little bit fresher. Hell yeah. And that's going to equal 1. This goes away. A is equal to 1. Got it. Next one, how about this? First row, second column. First row, second column. A times 0 plus B times 1. A times 0 plus B times 1 is 2. And so I see that B is equal to 2. Hell yeah. This value is in the second row, first column. Second row, first column. C times 1 plus D times 0 is equal to 0. So this is 0. C is equal to 0. And then we have solve for this value. Second row, second column. So we have C, second row, second column. C times 0 plus D times 1 is equal to 1. Alright, so that goes away. D is equal to 1. Alright, and what does this matrix look like? It looks like 1, 2, 0, 1. Hell yeah. And those look the same. So yes, any transformation to the identity matrix is just that transformation. And so this elementary transformation, so this elementary row process is a transformation to an identity matrix. So you have a transformation to the identity matrix is equal to an elementary row operation. I think this is how you would actually say it. This stuff just doesn't get, repeated in textbooks. That's why you have to go back and hunt for it. And a lot of textbooks are just like, well, the first time around you're not going to be able to understand it, so let's do some sample problems, but go back and figure it out. So that's what we're doing. Alright, hell yeah. So that just gets us the basic, but that isn't even the aha moment. The aha moment comes when we start to solve this problem from how they would have done it, and then we start solving it from using elementary row operations. So hell yeah, we're going to get a lot of room. Matrix, I always like to do this, keeps everything crispy. So we got 1, 2, 3, 4, 5, 6, 3, negative 3, 5. So this is our matrix A, and we want to turn it into an upper, where these values are 0. The first thing we're going to do is turn that into a 0. And so, and maybe we can start building, we can go through the process had we not known kind of all the proofs. What we're trying to build is a lower, and then we're trying to build an up, and then the upper is straightforward. That's just Gaussian elimination. That's the easy part. But then the lower comes from the proofs. The lower seems like hand waving. But when we build them, I would suggest building the lower over here as you're getting the values for the upper. Because then when you multiply these, A is just the multiplication of these. So this is going to be A after you do that. And so we can do a double check on reality. And then we have this much space to kind of work with. So the first thing that we want to do is change this to be a 0. And just think about how we do it from a practical perspective. Well, I want to multiply the top by something and then add or subtract. But I think that's where the hiccup comes in, because I'm just going to go over the mistake that I have made in the past. What I have done in the past is said, well, I just want to multiply the top by 4, and then I'll have 4, 2, 3 up top, and then 4, 5, 6, and then just this looks like visible subtraction to me. And so I can just be like 0, I can be like -3, and I can be -3. Did I do that right? 2 minus 5. But this, I would say, do not do. This is the biggest red flag you can do for lower upper. It makes your lower and uppers screwed up. Is because I think you're doing 2 elementary row operations at once. I'm not going to explain it, but how the textbooks do this is we're going to take row 2. So row 2, the modification again is row 2, plus, I'm just going to say plus here, plus some sort of multiple of row 1. And it seems like this could be, it could be switched around. But anyway, this will be for another video of why you can't do it in that way. I think it's just because you're taking this row and inverting it. It's almost like taking this row and multiplying it by -1, or it's like taking that row and multiplying it by -1. I just have to kind of walk through that process to see exactly what's happening, and then see how it would modify the lower and the upper. Okay, so so the elementary row processes, again, the elementary things that we can do are I can change one of the rows by a multiple. That's what that elementary row operation looks like. I'll say that's and then another elementary row operation that we're going to, because there's 3 elementary row operations. The third one is just switching. So I'm just going to say this is E2 star, and this is, E1 star, and this is E2 star. Not to get confused with E1, E2, which we'll be using later in this video. Or I can have my identity and then change one of these values. And I'm going to write it to what we're doing. So what are we doing? We're trying to change that value. If this was a 2 by 2 matrix, and I'm going to change that value, then that's an elementary row operation. It's saying that this didn't change, this didn't change, this didn't change, because I'm always starting with the identity. But that one changed. So it looks like this is what we're doing. And so this is the wild thing. What this would look like as a 3 by 3 is just, well, I have my identity matrix. I'm just changing that value. Everything else stays the same. This is the augmented. So I would take matrix A, and then I would augment matrix A by multiplying it by E3 star. I'm sorry, E2. And I'm just going to say this is, sure, E2 star, whatever. Hell yeah. But I'm just showing you that this is an augmentation of matrix A. You know what I mean? That's what, or it's a transformation. That's all. Anytime a matrix multiplication is happening, you're just taking the original matrix, whether it's a matrix or a vector, doesn't really matter, I don't think. But you are modifying it. You know what I mean? You're transforming it. Hell yeah. Gotta take my first break. Alright, hell yeah, we're back. And this is cool, because when we went through this process, we could have seen what we were doing to a row and the other row, but we're going to totally show it right here. So yeah, so this elementary row operation is a transfer. It's just a simple transformation. It does one thing, and that's why it's an elementary row operation. There might be more to it, but anyway. So, hell yeah, and that's going to be a modification of that. It's going to be one modification. I want to change one thing. Cool. And this is how we're going to do it. So let's do it. So we're going to take this, and then what number do I need to put in there? I don't know. You know what I mean? It's oh yeah, I want to. Oh, bummer. What are we doing? I want to change that value. Well, let's go. Well, actually, yeah, this is cool. You know, I'm hit a little hiccup. What does this row operation do? This over operation just multiplies a row by something. Is that what we need to do? Do I just need to multiply this whole row by 0 to get that to be 0? No, because I'd have a 0 all three there. I'm glad I actually said that, because sometimes, like using a tool, you want to see when it's useful, when it's not. So here's our other elementary row operation. And I just wish they drew it like this. And that's fine. We can. I think this is what I want to do. I want to say this. I want to change that value. This value used to be 0, and the elementary row operation made it 2. This value used to be 4. I want to make it 0. So, I mean, if this turned that into a 2, I should be able to turn this into a 0. And let's talk about this. What does this do? This value turning into a 2 says I multiplied by the other row by 2 and then added it to row 1. So hell yeah. No, I remember going over this today. I was just like, what does this elementary row operation do? So I'm gonna say this is my identity, and this is what I want to happen to my matrix. And so what did we? And this value is in, you know, let's say it's in row 2. No, row 1, column 2. So ij. So I is 1, j is 2. And then what are we actually doing with it? That's why this one's just so straightforward. Just multiply a row by a number. Who cares? But this one does like 3 things. I swear it does 3 things. One is that this is in row 1. Cool. And so this value is going to change row 1. So row 1 gets changed. So sweet. So I'm going to write this. Row 1 gets changed. How does row 1 get changed? We're going to take... okay, so we're going to start with... So row 1 gets changed by taking row 1 and then adding it to a multiple of row 2. So even if you use, like, you could say if this is the elementary row operation of aij, you could put these values in. You could say I'm modifying, this is the modification of row I by taking row I, adding it to the multiple of sorry, and I didn't do good justice here. So this would be row 2. By taking row I, the modification of row I is equal to taking row I and adding it to the multiple of, now it's still a row, but row j. And so this is an elementary row operation where this value is aij. And even though it's row, and we're using this j, even though it's associated with a column, we're using that value to say we're multiplying row j by that. So I think that is useful, even though I'm kind of slow playing this. All right, hell yeah. So that's what that does. Okay, so we don't want that. We we want this value to change, you know. And so let's talk about what that does. So this value is ij, and let's do it as a proof. So what is this transformation doing? It's changing row 2, so it's changing row I. So we have a change in row I. By taking row I, so it's equal to row I, plus a multiple, I'll leave that open, of row j. So sweet, this is row 2, this is row 1, and so this says, this elementary row operation, cool, yeah, because it only modifies one row, but this one's unique because it does a lot of different things. It takes some information in one row and then multiplies it and then adds it to another row. So this would be modifying row 2. So that's what we see. Row 2 is being modified. And how do we modify it? Well, we're going to take row 2, add it to a multiple of row 1. Hell yeah. So now, I mean, I'm still just probably a little bit on this one. I was just like, what are we doing? Because we're going to have a 3 by 3 identity matrix, and I want to change this value. Oh, perfect. Yeah. So this spells it out. Okay, yeah. I think this is just really good now. I can say this is, you know, some placement ij, and we know it's row 2, column 1. So it's row 2, column 1. I want to modify row 2, so row 2 is going to change. And we're going to have to change the entire row. But because row 1 is just zeros over here, those two values won't change. So hell yeah. That's why also an elementary row operation just changes. Does it by definition only change one thing? It seems like it. But okay, let's continue on. So our row 2 is going to be modified by taking row 2 and adding it to some sort of multiple of row 1. Hell yeah. And we could have said that by row I is being modified by taking row I and adding it to some sort of multiple of row j. See? And so this would be kind of like more of an equation for it of what's happening. So this is ij, this is row I, column j. And so it's row I is 2. So row 2 is equal to row 2 plus some sort of multiple of row, and this value is 1, row 1. Hell yeah. And so that's it. So what does that value have to be? I guess that's the interesting thing is, oh, yeah, no, this is tripping me out, because usually what we said was, if this is an elementary matrix and we did this to an identity matrix, like obviously we just, if this was an identity matrix, then we just get that transformation. Or if I had this this matrix and I wanted it to change that value. Oh, hell yeah. I'm so glad I did this, because it can only be one thing. So check this out. If this is the elementary row operation that I want to do, by changing this value, by multiplying it by the identity matrix, because I'm taking the identity matrix, I mean, this transformation can transform the identity matrix as well as just transforming matrix A once we get there. But it can only do one thing. This transformation can only change that value. And so, if you look at the identity matrix, yeah, no doubt. If I look at this identity matrix and I just say, hey, I want to change that value, can I multiply this row by anything? Hell no. I can't just multiply this row by 2 to get a 2 there. And that was kind of the elementary example. They put a 2 here, but how did you get a 2 there? I can't even use this third row. If I multiplied this third row by 2 and added it to this, you know, cool. Like this becomes a 2. So by saying I want to change this value, that really goes back to the proof of like, hey, I want to change the value of this value 1, 2. Well, I'm going to say that's ij. And so this value gets changed. The new, and the entire row gets changed, but the row I gets changed by taking row I plus the multiple of row j. But again, I'm sorry I went through that again, but just the fact that if I want to change this value, the only thing I can do is, I mean, I can just take this row and add it to this. I mean, you can always add a row to another row, and I like to think of it as adding instead of subtracting. And if I can multiply, I at least get to multiply the other row. That's the only way, like, you can change this value by any value. I can change this value by anything, any real number, by multiplying the first row and then adding it to the second. And that's what we have. And then, because it seems like that's what you're doing, how I just said it is I said I took the multiple of the first row, that's row j, and then I'm going to add it to row I. So sweet, because we're going to walk through this process, and this is probably the more normal way that you should write it, because that's when we do the matrix multiplication, that's the order that we're doing it in as well. And hell yeah. And then it's just a matter of like, hey, if this, so let's get a freshie. So sweet. So I know that I want to take matrix A, and we can even get this back just so you can see the example. But I want to take this matrix A and then do an elementary row operation. So this is going to be elementary row and I'm just going to say now this is the first elementary row operation I'm going to do on matrix A. 1, 2, 3, 4, 5, 6. 3, negative 3, 5. What I want to do in an elementary row operation, in the 2 elementary row operations that we can do, so I'm going to draw 2 identity matrix with modifications. So I'm going to do, hey, I maybe want to modify a diagonal, and then maybe I want to modify one of the zeros. So those are the 2 elementary row operations that I can do. I can modify the number of the diagonals, or I can modify the numbers of the zeros. That's another way to look at it. This is what but these are your 2 elementary row operations. You can't do row swapping, and so, I mean, it'd be just as simple to explain that, but I over-explain things anyway, so we can save 10 minutes on that. Alright, hell yeah. And thanks for sticking with me on this, because this is just kind of my first go-through. It's like I want to study at the coffee shop and then be able to like share what I understood, even though it's like you have to like kind of crawl through sand to do it. Okay, so I'm going to use one of these to modify that number. I can be like, well, no duh, I'm going to use that one. Now I just don't know what that value is. You know what I mean? So maybe I guess, you know, I mean, what I want this to look like, though, is 1, 2, 3, 0, 5, 6, 3, negative 3, 5. And if I know this is an elementary row operation, this is going to be 1, 0, 0. Don't know what this value is going to be, but 1, 0, 0, 0, 1. And so this is even so fast. I only have one unknown here. You know, this would be a good problem in itself. Is like, let's say I take this first row and first column. I'm going to call this unknown A. So I have A times 1 plus 1 times 4 plus 0 times 3. And second row, first column is second row, first, and that's going to equal 0. So hell yeah. So so I have A plus 4 is equal to 0, because this is 0. And I have A is equal to negative 4. So this is the back and forth. If you're doing matrix algebra, I would never stay away from the fact that matrices are equations. Like this is 9 equations, 9 unknowns. You know what I mean? Like here, always when you have two matrices being multiplied, this is your x. This is your unknowns. 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns. But you have 9 outputs. You have 9 equations. You know what I mean? 9 outputs means that you're, you know what I mean? And so hell yeah. And, I mean, if you don't know any of them, like if you're trying to find the inverse matrix, hell yeah, that sucks. But yeah, this is a perfect classic example of like always, you know, if you're just missing one value, this is really smart to do. Instead of just, I could have just hand waved and said, well, let's just guess negative 4. But now that's the value we're going to put in to that spot. So, so that's going to be negative 4. So let's do it how, let's say we just did the hand waving and said we know we need to put a negative 4 in there, and now I'm going to modify this matrix. And so now I'm going to do it, you know, how the matrix operation would have done it. And this elementary operation says nothing else changes except that value. So you can see that 1, 2, 3, 5, 6, 3, negative 3, 5, that all doesn't change. So let's go through every combination. This value 1 is first row, first column. So first row, first column, 1 times 1 is 1. 0 times 4, 0 times 3. So that's 1. Second one is 1 times 2 is 2. Oh yeah, hell yeah. 0 times 5 plus 0 times negative 3. So yeah, it's 2. Next one is 1 times 3 plus 0 times 6 plus 0 times 5. That's 3. So that was easy. Alright, so now, and you can do the whole process. So now let's actually see what operations we would do first. So if I want to find the new value in here, it's second row, first column. So I'm going to go second row, first column, and I'm going to do this first. So the first thing I do is take the multiple and then multiply it to row 1. And then I'm going to add, hey, and I actually add, I'm going to take a multiple times row 2. So I have 4. And then I'm also even going to take a multiple of row 3, but that's going to be 0. Times row 3. Hell yeah. And so, and that's going to be negative 4 plus 4 plus 0 is 0. So hell yeah. So that's what we get. This is going to be 0. But let's talk about what we did first. The first thing we did, and this right here is what we would call R2 star. This is our modification of row 2. And yeah. And because this is the modification of the entire row, let's do it for this value too, because this value changed. You know, we said 1, 2, 3 didn't change, but now this value, it didn't change, but we modified row 2, so it has the potential to change. So let's see what we do here. So this is in row 2, column 2. So we have row 2, column 2. We're going to multiply these together. So we have negative 4 times 2 plus 1 times 5 plus 0 times negative 3. Okay, hell yeah. And so this is going to be negative 8 plus 5 plus 0. And this is, did I do something wrong? Negative 8 plus 1. Second row. Oh, hell yeah, I did something wrong. No, yeah, this whole row changes. You know what I mean? So, yeah, even from the sample problem. This row becomes, this is negative 3, and this is negative 6. So that was just a mistake on my part. Yep. So this this elementary transformation will change this entire row. So even though the elementary transformation, the elementary transformation on identity. So if we took this transformation on, so if we took this elementary matrix, which is a transformation on the identity matrix, it's just going to change that location. But if I take this elementary matrix on just any general matrix, it's going to change this entire row. That row is going to change, but I can at least choose what one value in this row I want the value to be. So that's Gaussian elimination. I just like, well, this number's 4, let's get it to be 0. I could have said this number's 5, let's get that to be 0. Chill, you know what I mean? And you could, you don't, and even when we get to third row, I got to get both those to be 0. Doesn't mean I have to start there. So, hell yeah. So yeah, that's really good. I'm glad I'm going over this, because an elementary row operation does change that entire row, but it has this form, and if it was multiplied by an identity matrix, it would only change that value. And that's a little sneaky. And even here, this elementary row operation looks like it's just changing that value, but no, this would change. This would be multiplying the entire row, and what this one does is takes this row and adds it to a multiple of the other row. Or, how we're going to see, it takes a multiple of this number to the first row and then adds it to the second row. So hell yeah. So that's going to be -8 plus 5 is -3. And what did we do here? We took a multiple. So here's our multiple times that first row, row 1, plus a multiple of 1 times row 2. And that gives us row 2 modification. Hell yeah. So, and then we're going to try to find that value. So this is row 2, column 3. Row 2, column 3. So matrix multiplication is -4 times 3 plus 1 times 6 plus 0 times 5. And if we talk about what we're doing, we're taking that, and this was that starred value from that elementary operation. We're going to take that multiple, -4, so that's the multiple, and then multiply it by row 1. That's the first thing we do. That was the kicker to me. It's just like, why not, you know, why in the text would you write it the other way around? Why would you say row 2, and then I don't like this negative sign. So I would say row 2 is the multiple, and I would put it in parentheses, which is -4, of row 1 added to row 2. And I would even double up for juice, is that it's another parentheses. You're taking a multiple of 1 times row 2, and that comes out in the fact that you're doing an elementary row operation, where in that elementary process you're only modifying one thing. And then the number 1 is also being used in that process. Alright, am I just using these cards? Oh yeah, up here. Or where are we at? Yeah, we're modifying and we're using this. So this second row, third column, is -4, or the multiple, times the something in row 1. So -4 times 3. So yeah, you can just say -4 times 3, but what is that? The multiple times something in row 1. And then adding it to 1 times, we got 1 times 6, which is now just a multiple of 1, but times something in row 2, which just is the value. This is the value of row 2. So cool. And we do have a third one, plus 0 times 5. And that's going to be plus 0 times row 3. Alright, hell yeah. And I'm just trying to look visually, because we have the multiple, 1, and 0. And we have the multiple, 1, and 0. If we had like a 5 by 5 and the elementary row operation was 1, 1, 2, 3, 4, and then star, well, no, let's do 0, 1, and then we had 0 star here, 1, 0, 0, 0, 0, 0, star, 0, and then 0, 0, 0, 0, star. So if this is an elementary row operation, sorry, that should be 0, and that's the value that we're changing, is that this would act on a column, you know, so this would be row 1, row 2, row 3, you know, so on. So this would, and this is row 3. And because this is an elementary matrix, row 3 has this value 1 in it, but you put the starred value in, you know what I mean, the second place right here, and that's where this star value is going to have a location 3, 2. So that's where we have I is equal to 3, J is equal to 2, and so that's why the J is what it's modifying, if I'm saying that. Hopefully I got that right. Yeah, because we're doing the multiple. So if we write the proof again, we're saying that this elementary row operation changes something. It changes the I value of where that elementary you know, thing is. So we're changing row 3, and that's going to be a new value for row 3 by taking, and we'll do it as we're supposed, you know, like I'm trying to do it. We're going to take that multiple times row J, and so that's where that 2 comes in. So if this is right here, it's a 3, 2 location, and the 2 is important because that's the row that it's modifying. That's why all the other rows will be zeros, and so that's why it just gets neglected even from a textbook. You know what I mean? And that's why even this just seems like you're stacking numbers and doing some sort of just, you know, like we all do, two equations where you're subtracting 2 equations. Having this thing go on. You know what I mean? We're just, or this one. I'm just going to take 2 equations and put them on top of each other and then add them or subtract them. But this is the type of stuff that you want to see what's happening from a location-oriented, you know, proof. Hell yeah, because that really shows that, because you're going to get bigger matrices, and you're going to say, hey, I want to modify this value, and, you know what I mean? And that's why we do a visual. Well, it looks like these 2 equations are stacked, and so I'm going to take one equation subtracted from the other, you know, quote-unquote subtracted. But, you know, that's the trouble that I got into, because when we do LU, if you do this subtract that, you're going to get a bummed up answer. It'll be for another video of fully explaining that. If you always just add, but then if you add the, if you multiply this row by the multiplier, that's also fundamentally wrong from this elementary perspective. You know what I mean? If you multiply this row and then add it to that, oh yeah, look at this. This value is up there. So that is kind of the kicker. Like if I'm doing that process, the elementary row operation is just that gets transposed. And so those are the things that's real fascinating to me, to be like, okay, I did it this way and I got the right answer. You know, for a lot of things, like what elementary operation am I even doing, and why is it not working with the other, you know, with the way that we're supposed to be doing this. Okay, hell yeah. So that's why this gets dropped out, and I think I explained that enough. And then hell yeah, and since we just have a huge typo on the board, let's do this. Elementary row operation, start with an identity. I want to change this value. I'm just going to know to change it to that. How would I know to change it to that? Well, I mean, a few things. Like I can go back to just, hey, these are 2 equations. I want to, And I know if I'm going to modify this, I have to take a multiple. That's what I've learned from this. And the elementary row operation is modifying the other row and then adding it to the row you want to change while keeping the other row the same. So that kind of fully should explain also of like if I did the, something and I got 3 equations, now which 2 do I use and what the hell does that even mean? But yes, that's a good way visual that I need to multiply this. And if I just want to do straight addition, if I do this line here, I want to multiply this first row by -4. Hell yeah. And that is the elementary thing that goes into our elementary transformation. I'm going to transform matrix A. And hell yeah, the first row doesn't change because of those 2 zeros. So we got 1, 2, 3. Let's do the last row. So hell yeah, 2 zeros there, so it's just 1 on that. So that's pretty sweet. 0, 0, and then we got -3. Alright, hell yeah, 0, 0, and then we got 5. So all the juice is happening to this, and then we're just going to kind of walk our way through it. This multiple times row 1 is -4. Plus the multiple of 1, or just row 2. So that's how you would see that, or just row 2. Hell yeah. And then the other row is going to be 0 because we talked about that hopefully enough. Hell yeah. And then you're going to get that thing's going to be 0. You got to do this to each one of these values. The multiplier times row 1 is going to be -8 plus row 2. -8 plus 5 is -3. The multiplier from the elementary thing, thing that you want to do. That multiplier times row 1 is -12 plus row 2. Gives you the new value in row 2. So that kind of, and then -12 plus 6 is -6. Hell yeah. So now we get into the complexness of forming a lower and an upper. So, and I'm going to call this E1 now. So E1 is a very specific matrix that I shouldn't have boxed it in, but we could say E1 is, I'll do this. No, I think, I don't know. But yeah, E1 is, put matrices in kind of parentheses. It's always kind of a good thing to do. Anyway, or it looks like a matrix. So we have this elementary row operation that we did to matrix A, and now we have our first modification. I'm just going to call it upper star because it's not the upper, but it's the first thing that we did towards, we're trying to work towards making this the actual upper matrix. And now you can see that we took this elementary thing times A, and guess what? This elementary thing times A is a new matrix. Like this is E1 times A, which is its own matrix. So this is E1 times A. In this order, multiplication of matrices is associative. I can put, once I got 3 of these things, you can see that I can put the brackets anywhere, but I have to be traveling in that direction. It's not commutative. I can only go to work. On the way, if I try to get home, I'm gonna be lost. Okay, hell yeah. All right, so now we want to do our. Then I'm gonna take this new matrix, and then hey, we're gonna do some other sort of elementary row operation. But now let's get into the proof because might as well, so you can have that rolling in your head. Because at the same time, so we're starting to build our upper. The upper is gonna be. That's never going to change. We have a 0 here, and then the diagonal might change, but I'll just cross out the numbers. But these are going to change. Hell yeah. But I don't know. If I'm doing this on paper, I'm at least going to do this step, maybe. I don't know. Maybe bummed it up. Okay. So how do we build the lower? The lower says we start with the identity matrix, and whatever we did Like the lower says if we multiply, this used to be a 4, and we multiplied the top row 1 by a negative 4, and we're changing this value. If I'm changing this value, the lower, this value gets changed in the lower. Why? Well, hand waving says if I have this multiple of negative 4, I'm going to put the opposite right here. So this is going to be positive 4. This used to be 4, 5, 6. So you could just say, oh, I'm just going to put a 4 there. You know what I mean? That's always going to be the case. Probably, usually, as long as you don't do any other elementary row operations. But we want to know why that is the case, and so now we're going to explain why. And I might just grab just a big sheet of paper. Okay, so let's see if I've never even done this, but all right. So we have A is going to be a lower and an upper, and then and to get the upper, we're going to take E1 times A. And maybe we're just there. You know, if it's a 2 by 2 matrix, and here's some values, you know, maybe this was a value, but I multiplied it by E1, which modified that row, and that row became 0. So now I have an upper matrix. So maybe I'm just good to go. So I would say that is the upper. We could even start there. So EIA is going to be the upper. And so, yeah, because, yeah, the proofs are all hard, I think. For me, they're hard. But, like, what's one thing we can do to this matrix is, oh, yeah. I'm just going to play around a little bit. Because if this A is the lower times the upper, I could say A is lower times E1A. Does that help me out? Probably not. Oh yeah, what they say, yeah, for the proofs, usually the proofs involve some sort of identity sometimes, and this one does. So that's like, you know, I'm just trying to figure, if I was on a desert island, I was just like, well, why, where are we going? It's the identity. So what we know about any identity is A times the identity, or inverse A is I. And I would actually write this the other way just to be like, hey, it could be this way. It doesn't really matter. This is the only one that is commutative, the identity matrix. Other matrices could be commutative, but no guarantees there, right? And so, hell yeah. So now what we're going to say is U inverse U, or typically you'll do it this way. The textbooks will always do the inverse out there. And then what they're going to say is, hey, I'm going to take the inverse of, yeah, how are we actually doing this? Yeah, let's, yeah, because this is good to be like, hey, what the hell does the textbook even say? And, you know, you want to see this first instead of me just making stuff up. So what do they have here? Well, this already shows the proof. They say that the lower is this, and that's what we're going to get to in a second. But why is the lower that? You know what I mean? It's because what we did is we got the upper by doing all these elementary things. So we can really simplify. Anytime you see a K, you're probably going to lose your mind, you know what I mean? But that's all we did. We took that first elementary thing and we multiplied by A, and then in a 2 by 2, hell yeah, we got the upper. Congratulations. And so now, what's the first thing they're going to do? All right, hell yeah. I took a 20-minute break and kind of see what they're doing here. And so let's see if I can put it aside and go for it. So the whole premise is that we can take matrix A, and this could be thought of as any matrix. Any matrix can be a multiple of two matrices. And why would that be the case? Is because you could always take matrix A could always be matrix A times the identity matrix. So, you know what I mean? We can have matrix A times an upper. You know, we can always craft an upper matrix. And so now this should also prove like probably why the upper has to be in this location. So what did we do to matrix A to get the upper? We took an elementary operation, which is a matrix in itself. So we took a matrix times A, and we're just going to say, hey, that was good enough, and now we have an upper, because you can do this to a 2 by 2. We just showed that. But now what I'm going to say is, hey, I want matrix A. You know, and I think the confusing thing is cool, we can get an upper. Let's say the lower, we don't even know that it is a lower. We're just going to say it's another matrix. So let's see if that works. Because I'm gonna say matrix A is some sort of matrix, just B, times the upper. Cool. And yeah, I don't know if I want to do that, but what we have here is matrix element, and you might see this just faster than I do. I'm just trying to, like, if I was on that desert island, you know, I know I can get there. I'm just wondering, like, you know, what's my mental process to do it. Yeah, so I know that this times A gives me the upper. I know I can take an inverse of both sides of a matrix, so that's what we're going to do. We're basically going to say inverse of this elementary row operation on both sides is A again. And then, so let's do that. So, so we're going to scribble that out. So I'm going to take inverse of E. And now I'm going to kind of ditch the, well, I don't know, it's kind of, well, yeah, let's kind of ditch. So we're just going to do E1 inverse times E1 times A is equal to E1 inverse times U. So all I did there was did the same thing on both sides of the equation. You know, I mean, we should be chill. And when I take an inverse times, you know, inverse A times A is always A, just in a generic sense. Inverse B times B is always B. So inverse E times E. And what the hell am I even saying? No, this is the identity matrix. Sorry about that. So yeah, inverse of a matrix times itself is the identity matrix. Inverse B times B is the identity matrix. And yeah, and that's why these proofs are nice, because you can kind of do them in steps. So this is what I'm going to do first, and I'm even going to put parentheses to show you the associative properties. You know what I mean? Because even here I could have multiplied those two first, but we're going to do those two first and get the identity times A. Over here we just have, we don't know what's going on yet. Identity times any matrix is just that matrix. And again, we kind of showed that today too. This is still two matrices being multiplied together. We get a new matrix, call it A prime, but what we find is A prime is equal to A. And so therefore, you know, this multiplication is just the original, it's just A. Hell yeah. So identity times any matrix is that matrix. So now we have A is equal to E1 negative, this elementary row operation, the inverse of it, times the upper. And now we have something that looks visually like A is equal to LU. You know what I mean? Right here, that's the kicker. So you're like, oh, well then L is equal to that. Yeah, I don't know what kind of proof this is, other than just being like, no duh. And so, hell yeah. So the lower is going to be the inverse of the elementary row operation. So now I think this is in my studies, I was just like, well, let's figure out what the inverse of a row operation are. So let's go back to those elementary row operations. You know what I mean? And we can just know them by heart now, because we have an identity matrix. One thing we can do, one elemental row operation, is change a diagonal. So I can even change that one. I'm just going to do one at a time, you know, just to show. I'm not going to put two stars on both of them, but I can change that value. The other elementary row operation I can do, I can change one of the zeros, but just know you change the zero, not by multiplying that row, but by doing something to the other row, right? And then adding it to it, and then keeping the other row the same. So that's what went on. And now what's the inverse of something like this? Well, the inverse of any matrix, so the inverse of any matrix is 1 divided by the determinant of that matrix times the adjoint of that matrix. And again, I haven't gone through this 100%. I'm just kind of knowing this is what they told you in the textbook, so why can't we apply it to an elementary matrix? It should be the easiest thing ever. And there's a lot of stuff in physics, engineering, math, where you just forget to do that complex thing on the simplest unit. You know what I mean? Because that actually is kind of a mind trip. You know what I mean? Integrate, do this in the most complicated way possible. This is going to be x equals 1. This is y equals 1. And integrate that area. You know what I mean? And using, you could use this as your equation, y is equal to 1. You could use this as your, and then you're going to have to use this as your equation too, x equals 1. Because it's a double integral. This is the integral of dA, which is double integral. And it's, bounding between, and this actually is x equals 0. That's the line x equals 0. Sorry, y is equal to 0. This is the line x equals 0. And then so your bounds are x and y, dx, dy. But that lower is going to be x equals 0, x equals 1. And those are lines. They're not just, just points. They're not just like evaluating something at a point, even though it could be thought that way. But hell yeah. It's bounded by y is equal to 0 to y is equal to 1. And then you can easily, take the integral of 1 times the integral of the other. This only portrays to that, so it's just going to be x0, x1 dx, and that only portrays to that. This needs to be done a lot more in calculus, is like constants get rid of, whatever jives, and now you can, especially if you have... Anyway, yeah, so then you're just like, anyone can do that. It just goes to x, evaluated at 0 to 1. But yeah, these seem like points or something, you know what I mean? Not lines being bound. So that is, sorry about that, but that's just an analogy for stuff like this. It's like, it's hard to take a complex thing and apply it to the simplest unit, just the simplest problem I find. Alright, hell yeah. And what the hell is the adjoint? It's the cofactor transpose. We'll get to that in a second. But the inverse of this elementary matrix, the determinant is always going to, well, it's the multiplication of the diagonals. There's a lot of ways you can think of the determinant. And so the multiplication of the diagonals, or it's this times that minus 0 times 0. So it's just that value. Now, the adjoint of A is the cofactor transposed of A, which is the minor... is the determinant of a 2 by 2 matrix... no. Yeah. We know what the determinant of a 2... What the hell's the inverse? Inverse is 1 divided by the determinant times the adjoint. How do you take the minor of a 2 by 2? Is that even possible? I'm kind of losing my mind. I know it with the 3 by 3, but yeah, because if you were trying to find the minor of that location, well, you're not left with anything else. Hell yeah, and that's exactly why this is crazy. Like the simplest thing, finding the inverse of a 2 by 2 matrix using this formal definition ain't jiving for me right now, so I'm going to go on Google. Booyah. Alright, hell yeah, that was the best 5 minutes of my life. Yeah, you can, a 1 by 1 matrix has a determinant. You know what I mean? So I'll just make some 1 by 1 matrices and we're going to find the determinant. So, or has inverses. Inverse. So this has no inverse because the determinant of this matrix is 0. The determinant of this matrix is 1. The determinant in this matrix is 3. The determinant of a 1 by 1 matrix is just the value. Because we're going to use this adjoint process. The adjoint is the cofactor transposed. The cofactor transposed is finding the cofactor of each of these locations. The cofactor is the minor of that location with the sign change. So these diagonals, depending on the ij, the formula is -1 to the I plus j times the minor. So the minor of this location is crossing out that row and column and finding the determinant of the remainder matrix. We're left with a 1 by 1. I didn't know that you could do a 1 by 1 matrix. The textbooks for sure just classify everything down to this 2 by 2 and then you kind of call it good. But the determinant, and that's where I think even in the textbook they have a separate definition for the determinant of a 2 by 2 matrix, which this should still apply. So we're going to derive the inverse of a 2 by 2 matrix by just using the standard definition. Hell yeah. So here it goes. So we need this adjoint, which is the cofactor transpose. We're going to find the cofactor and then transpose of it. But first we're going to find the minor, and knowing that the... So yeah, if I want to do this in texty fashion, I don't know if that was an adjective, but I want to find the minor of this location. Row columns goes away, and then find the determinant of the remainder. So that is the minor of that location. Minor of that location is 0. Minor of this location is 0. Minor of this location is that value, that modified elemental change. This is the minor. The cofactor is the fact that this is positive, positive, negative, negative. Okay, so in this case the minor is equal to the cofactor because negative zeros don't do anything. And then the cofactor transposed of this is just the transposition of it. Because it's a 2 by 2 matrix, only the diagonals would transpose, you know what I mean? So it's the same. Or you could say I'm going to write this row down this column. So this row down this column, this row down the next column. And I'm left with the same thing. Sweet. So I'm going to take, so the determinant of a 2 by 2 matrix is that matrix divided by its determinant. Okay, the determinant of this matrix is star 1. Yeah, that's interesting. So the inverse, and that's almost really similar to what an inverse is, because we're going to get that value divided by this. So the inverse of this matrix, the inverse of this matrix is 1 divided by the determinant of that matrix. And then divided, like multiplying this through, we're going to have 1, 0, 0, and then this will be 1 divided by that. So that is the inverse. So that's interesting. Here's the original matrix, here's the inverse. Hell yeah. And in this case, we also did something kind of unique. We took... yeah, I don't know how we got down on that tangent, but, yeah, because I was just like, well, the lower is the inverse of that. So if we did this one little thing, you know what I mean, which we did, so hell yeah. So, so let's say here is our identity matrix. Here is, and what I want to do is, so here's our matrix A. I want to change that value, which we do in Gaussian elimination. And in this case, it's already 0, so I'm just going to change it to a 2. So we know we have this elemental operation. We know that there's 2 elemental operations we're going to be using for LU substitution. One is changing a whole row. The other is changing a value in a row by multiplying it by the other row. So we got, and then adding them. So those are the 2 things. I want to change this to 2. Hell yes, we're just going to use real numbers for this. And so that's going to be, yeah, this one. So 1, 1, 0. This is the elementary thing we're going to do to A. And when we do this, we're going to get 1, 0, 2, 1. We need to actually put some sort of juice in here. So what we're going to just make up our own. So we're going to say A is, I don't know. Well, let's see, what should we make this? Yeah, let's say it's 4, 2, and this is 1, 1. Hell yeah. And I want to change this value to a 0 by using an elementary row operation. I know this is going to modify the first row, so this value is going to be negative 4. Few ways to figure out knowing what that value is, or just hell yeah. So this is our elementary row operation. When we do this, we get the upper. So hell yeah. And let's go through that process. We're going to have 1, 0 up top. This value is going to be 1, 0. So the top value doesn't change, and that kind of shows that this elementary operation does not change that top row. And then we have negative 4 plus 4. This becomes 0. And then we have negative 4 plus 2. So this is negative 2. So there we go. We have our upper. We have our elementary row operation. What we're going to do is we're going to take the inverse of both sides. That's where we are on our proof. And if we do that, we're going to say this inverse is the lower, because lower times upper, this is the identity, and that has to equal A. So this will equal our lower matrix. It's not so obvious with a 2 by 2, but hey, that's an upper, and we got a value right there. So let's figure out what the inverse of this matrix is. And so we're going to say the inverse of a matrix is 1 divided by the determinant of that matrix times the adjoint of that matrix. The determinant of this matrix is 1 times 1 is 1 minus negative 4 times 0. So it's just 1. Hell yeah. And then the adjoint, well, I mean, we can do this as a side. Let's find the minor first, maybe. Keep it simple. The minor of this location is 1. The minor of that location is negative 4. The minor of that location is 0. And the minor of that location is 1. The cofactor is those locations. These don't change, but because this is in row 1, column 2, negative 1, 1 plus 2, that's going to be negative 1 to the 3 times the minor. That's going to be negative 1 times the minor at that location. So that will have a sign change. 0 doesn't have a sign change, but it would if it was a value. So that's the cofactor. Then the cofactor transposed is either this row written down this way, and then this row written down this way, or just flip-flopping these values, where on this diagonal, those diagonal values stay the same. Okay, hell yeah. And look what we're left with. We're left with a lower. You know what I mean? So it's 1 times that matrix multiplied through this scalar, and we're left with 1, 4, 1, 0. All right, booyah. So this is our lower, which is also the inverse of that elementary row operation. That elementary row operation is what you call it, of our matrix. But it's the first transformation. I'm going to call it a transformation of A. Hell yeah. And we walk through that process. Transformation times A builds the upper. These two multiplied together is the upper. Take the inverse of this. That becomes an identity, but you got to take the inverse of both sides. Now we have A is equal to 2 matrices multiplied. And there has to be something where when you take the inverse of both sides, they're in front. Yeah. Because if you put the inverse, yes, yeah, this is fascinating. This is another one of those fundamentals. I can multiply, if I have this going on, I can multiply both sides of this equation by a matrix. But I could either multiply this, I could stack the matrix on this side, due to the commutative property, and the fact that there is no commutative property. Commutative property says you can go back and forth, but this is going to be drastically different than taking a matrix here and multiplying. And if I took inverse E and multiplied on this side, I would have A times inverse of E, which I don't know what the hell that does, and then E times A times inverse E, who knows, so you get something drastically different. And so upper times this inverse E is for sure going to be a different value. So that's also that's what I just kind of realized, is that for sure, even from these proofs, when I multiply both sides by the inverse, it's probably typically always, or maybe always putting the inverse on this left side. Or strategically up against something where you take the inverse times it can make it an identity. But that also, sometimes I might want to make this, I want to maybe make A an identity, but I still have a string of transformations on this side. So I would multiply A inverse on this corner, but I would have to come to this corner to multiply by A inverse. So that is a property that I can see from, just kind of like what's going on in the textbook. So that's pretty sweet. All right, hell yeah. And just for kicks and giggles, we got this lower, and then we have that upper, and then hopefully when we multiply them together, we're going to get A, which is this. This was the A that we started with. So 1, 0 is 1. This one, 1, 0 is 1. This one, 4, 0. This one is 4 minus 2. 4 minus 2 is 2. And hell yeah, we have a check on reality. And I think that was good. I'm so glad I actually walked through that, because my analogy right here, it held. I didn't know a 1-by-1 matrix had a determinant. I didn't know a 1-by-1 matrix was invertible as long as its value is a positive number. The whole idea with inverse is that if the determinant becomes 0, it has no inverse. And I kind of glanced through the proof there of like how you find determinants. It must rely on a matrix that is linearly independent. And so, like any matrix, you can use Gaussian elimination. I don't have to have a solution x is equal to b over here, but I can still take this and do elemental steps. And using Gaussian elimination, I can get this value to be 1. I mean, because this is invertible, has a determinant, and can, invertible means take the inverse of, I can use Gaussian elimination to get 2 zeros there. And if this is 5, I'm just going to divide this row by 5. Elementary row operation, I can get a 1 there. If I can get a 1 here and a 0 there, well, then I can easily, get that value to be a 0. Because, I can just multiply this. I'm going to modify that row by multiplying this and then adding it to that row. Hell yeah, and then that would go away. It won't have anything to do with that diagonal. But elementary row operation says that, well, and then again, if I just have 0, this number, and this number, it's as if it is equal to maybe, I can always divide to get it down to a base of 1. So I got a 1, 1 there. And then if I get a 1 here and a 1 there, I can make that 0 and that 0. So that's the Gaussian elimination process of getting these to be 0, getting your upper, and then going back and getting those to be 0, and getting this to be 1, 1, 1, which is your elementary, which is your proof that this matrix is independent. That these are independent equations. I don't have a 1 here and a 1 there where those would cancel out. If I had 2 rows where this was a 1 and this was a 1 and 0, 0, 0, 0, I would have a redundancy of and I could just subtract those equations, use that elementary row operation, and one of the equations becomes 0, 0, 0. You know what I mean? This would be 0, 0, 0 if this one stayed the same. And if you get a row with zeros, then you know you have yeah, is that true? That then you're... Oh yeah, because I'm confusing diagonals. Because I was just like, well, if you get a row of zeros, that happens all the time in an upper and a lower. Well, sure. Rows of zeros mean that you can... Wait, what the hell does a row of zeros mean? If this is a 3 by 3 and I get a row of zeros and a 1 there and a 1 there, then when I do my determinant, the determinant 0. Oh, that's interesting. Oh, but an upper and a lower doesn't have zeros all the way across. It'll always have one value. That's what I was confusing. So when we do our determinant, yeah, I only have 2 zeros and then still a value. So yeah, determinant on an upper and a lower. So when we form an upper and form a lower, those will always have determinants that are positive. So yeah, you can't... Yeah, that's fascinating too. This must be a proof where you can't take a matrix and decompose it into 2 matrices where you lose your determinant. You know what I mean? Both of those matrices are still independent. Hell yeah. Alright, so now let's walk through the juicier part of the proof. Because, I mean, what we're going to do is we're going to do a bunch of elementary row operations to this. So I'm going to have this matrix A. The first thing I'm going to do is transpose it by doing an elementary row operation. I'm going to say this is the new matrix, parentheses there, and then I'm going to do another elementary row operation. So the first elementary row operation was to get that to be 0. That's that one. The second elementary row operation is to get this to be 0. That's that one. Cool. Let's say I was done there, but I mean, well, let's do them all, because we're going to have 4 elementary row operations. Then the next elementary row operation is I want to change, and in this problem you don't have to, but it's good to work both of those 2 elementary row operations. I want to change this to a 1, and so I'm going to multiply this row by a scalar, and that's an elementary row operation. So that's going to be elementary row operation number 3. Once this becomes a 1, I'm going to make this a 0 by making this a multiple of 3 or something like that. So that's going to be elementary row operation 4. Once I do that, I have fully crafted my upper matrix. So I can say this is an upper matrix. Hell yeah. And then what I'm going to do is take the inverse, and then so I can always put my parentheses anywhere. These are associative. I just know that I have to multiply in this direction, but I'm going to box those in associatively. Association, groups, groups by association, associative property. And so now I just want A to be something U, because our whole gist is to get A to be LU. A is equal to LU. Cool. We already got U. We're going to take the inverse of both sides. And this is where it's going to get, this bracket this inverse has to be around everything, and then we're going to have to use a special proposition, and that's the one that I said I was going to wait to this part in the video to go over. Because, yeah, it's fascinating. And the only way I can prove it is just by guessing and making sure the guess worked out, and then guess wrong, and then show that the guessing wrong does not work. And I think that, I swear reading this textbook, some of the proofs were just like, proof by that. You know what I mean? Try some, I don't know. Yeah, I shouldn't. Anyway, hell yeah. And then, whoops, my bad. So now this thing is going to be the inverse, so we're taking the inverse of both sides. Hell yeah. And that's U right there, which we've already found. We've showed that. And this becomes the identity. So this right here is the identity matrix. Identity matrix times A. So then, therefore, that entire thing just becomes A. So we have A is equal to this. Now, it seems like, well, why can't we just do the inverse of 4, inverse of 3, inverse of 2, inverse of 1 times u? Why can't we do that? Hell yeah. Alright, so yeah, I'm trying to figure out, yeah. So, I mean, so what we have here also is kind of interesting. We can kind of take a pause. If I'm saying this, this is A is equal to this, but we can even take a step back and be like, what if I took the inverse of an inverse? You know what I mean? Let's say I took that's one way to look at it. I could take the inverse of an inverse. So I could say like, hey, this is the inverse of this, and I want to take the inverse of that. Well, that's kind of a redundant way, but I could just say, so what I'm going to propose is that, and this is the proof, I'm going to take this out of my equation and say that the identity, if I do take the inverse of all this, which is just these values, you know what I mean? You could see this is the inverse of A, and A is in there. Well, what if I just took A times the inverse of A? Then I would get the identity matrix. So inside this bracket is, what we're claiming to be A. This entire thing is A inverse. So let's write that out. And so we have E4, E3, E2, E1 times E4, E3, E2, E1 with this bracket that says inverse. And we're saying this is the identity matrix. So now is the point where I get to choose what to do with this. And it should already be evident that if I start to break this up into individual things, like associates, or I'm just seeing it from my perspective, I can group those two. Like everything has to still be in this order. Not these. I can rearrange. If I'm saying like, hey, this has to be like inverse of 4, inverse of 3, inverse of 2, inverse of 1. I'm just hoping that if I multiply those together, hopefully that's the inverse of this entire thing. And maybe one way is just to guess this way, which is wrong, and that's what I'm going to show. Because if we have E4, E3, E2, E1, and then E4 inverse, E3 inverse, E2 inverse, E1 inverse is equal to I get to reduce this thing by putting my parentheses around stuff, but what am I going to do? Am I going to put my parentheses, and I know a matrix times an inverse is an identity, but these two matrices are different. I have no idea if those are going to be an identity, and that doesn't fit the proof. Even if they were an identity, it doesn't fit the proof for all matrices that are different. So this is just not jiving right off the bat. So what I'm going to say, so that's not jiving. So I'm going to say that the inverse of this is just the order switched. So I'm going to switch the orders there and switch the orders there. So I have E4, elementary row operation 3, 2, 1, multiplied by inverse 1, inverse of elementary row operation 2, inverse 3, inverse 4 is equal to I. So yes, so I'm saying that this thing right here is equal to this thing. But I can put brackets there if I wanted to, just to say that those, so that was the deal. We're saying that this is the individual inverses, but we have to switch the order. And I'll try to go more into the proof of that, but I think even just kind of seeing it from the visual here, that now I can group those two together. This becomes the identity. And because it's the identity, I can say, the identity times E2 times the identity, or this identity times E2 inverse is just E2 inverse. These two multiplied together is just E2. So, you know, in the next step, then you can just get rid of it. So hell yeah, so that goes away. Then put the next brackets around those. This is an identity. Cool. By that same process, the identity times this or the identity times that just makes this go away. Next bracket will go around there. And so hell yeah, that's the identity. Identity times this, the identity, it goes away. It's just these two. And then these two are an identity, and then so we have an identity is equal to an identity, and then you lose your mind to be like, what were we even trying to do? Well, we were guessing that this structure right here was E1 inverse, E2 inverse, E3 inverse, E4 inverse. That's what we were hoping. Hoping that these, now we know that the inverse, if we have like a bunch of matrices multiplied together in this order and we want the inverse of them, then it's going to be the inverse of each individual one in the opposite order. Alright, hell yeah. So now let's go back and see how that proposition applied to our matrix A. So our matrix A required 4 things. E1 made that 0. E2 made that 0. E3 turned that into a 1. And E4 made that 0. We finally have our upper. This is equal to our upper. I'm just going to give a lot of room. I want to know what the lower is. And I know that A is equal to the lower times the upper. So if I can get this A by itself over here, I'm going to do so by taking the inverse of this group, E4, E3, E2, E1. Inverse on both sides. Okay, hell yeah. So now I'm just left with A. So A is equal to this. By that proposition that we just proved, I'm going to say this is E1 inverse, E2 inverse, E3 inverse, E4 inverse, U. And now I have something in this form, and by the no-duh proposition, I can see that L is equal to E1 inverse, E2 inverse of elementary row operation 2, inverse of elementary row operation 3 and 4. So that's what the lower is. The lower, and then in the text they say while you're making the upper, you know what I mean? While you're making the upper, you're making the lower from an identity matrix. Which, if you're making the lower from an identity matrix, it means that you're multiplying that, you're doing some sort of elementary row operation onto that identity matrix to get that value. If you take this identity matrix and say, I want to change this value right here, well, you didn't change a diagonal, so you didn't do a multiplication of a row. If you change this, the only way you're going to actually get something is to modify this. So you modified that by a multiplier and then added it to this row and then kept this row the same. So right there you did a elementary row operation. And what we're showing is that, okay, yeah, and go back to it. We started with an identity matrix. That's the cool thing. This is one of the cool properties of the identity matrix, maybe, is because since we're saying we're starting with the identity and building on it, I can put the identity matrix anywhere. And this is where, if I put the identity matrix here, I can already start building my identity matrix after I have done the first operation. So in this process, when I did this, took my elementary row operation on A to get rid of this 4, I know what I did there. Let's walk through that. Because this is a 3 by 3 matrix, I changed that value. Didn't change I didn't multiply a row. Can't multiply this by 0. Can't do that. But I can multiply something else and add it to this while keeping that other row the same. So this is the elementary row operation we did. And this is E1. And this E1, just for writing it out, was a negative 4 Cool. So that was elementary row operation E1. Because I did E1, I can know by this proof that part of the lower is going to be the identity times inverse of E1. And so that's why you can start to build the identity matrix. You can start to build this lower. So this is the lower, this is the upper. And that's why you can start to build right after you do that. You could wait. Yes, and is there any other way to do this? Because if I did all these transformations, E4, E3, E2, I could group them up. Yeah, that's the other way. If I stack these, if I say, cool, if I just keep track of the matrices, E1, and then multiply it by E2, and then have this new matrix, and then multiply by E3, have a new matrix, and then multiply by E4, what I do get is I do get that. This is that. And then so if I do get this as just a matrix of 9 values, since that's what we have, a 3 by 3, then I can take the inverse of that. But I think that gets, and that's just going to be a lower, it's going to be a lower anyway. So yeah, these elementary matrices do not affect, I'm never putting a star into these upper quadrant. So these elementary matrices always make a lower matrix. These uppers are always 0 because I never put that star into, I never modified those values at all. So yeah, so then I would just have the inverse of a lower matrix. And then I kind of lose my mind what the hell is the inverse of a matrix? Well, the inverse of this, yeah, the elementary row operations. So I'm gonna call this EL because it's a lower, but it's the elementary row operations that helped us build the upper. By getting Gaussian elimination, getting rid of the values in A. Alright, hell yeah, we're back. And new battery, took a little break. I always forget where I was. But we crafted all these elementary row operations is just this one matrix. So if we took this one matrix times A, we would craft the upper. And so, but to find the lower, we have to take the inverse of that. And so, and then I was just thinking during the break, is just like the whole point that the aha moment of this is every time we do a element, and now I can know it as elementary row operation. When you're just doing like, hey, I just want to modify that to be a 0, you're probably not calling it an elementary row operation, and I won't anyway. Just do what you do. Do your thing. But now, if you're going to call it an elementary row operation, just know that it is a matrices, and it's a transformation of another matrix. You're taking a matrix and transforming it. Cool. And you can just keep track of that. So if I want to change that to 4, I know it's not a diagonal. I know I'm going to modify it right there. The modification is a -4. I'll try to make better videos on like why it's -4. I'm still just going back to the fact that, hey, I got to, well, if I'm putting the value there in my elementary matrix, the only matrix I can modify is that one. And so therefore, it's a -4. So the value that I put in that elementary matrix has to be the multiplier of this first one, and then I always think adding. You know what I mean? So I'm going to multiply it by a -4. Cool. And, hell yeah. Alright, so that ain't bad. But then I'm going to keep track of that matrix. That elementary matrix, that's the first thing we did. That's E1. And then, so once I get E2, like I said, you could multiply E2 times E1, just to do that, to keep track of that. I just wanted to show that when we build the lower, you don't have to start over here. You could have worked backwards. You could have kept track of, yeah, we're keeping track of each thing we do. Like, I know what that matrices look like, E1, E2, E3, E4. But when we, and I guess I need to know, I know the lower now from this equation is the inverse of those. So at any point that I do an elementary row operation, like the first one, again, the first one, and let's write this out, E1 was -4 right there. We have the identity matrix. That's E1. The inverse of E1, you know, is going to be 1 divided by the determinant. The determinant's the diagonals, you can think of it that way, is 1. Or the determinant is actually, the determinant of this matrix is this value. You pick a row or column of values. You take that value in that, you know, I'm going to do those three, 1, 0, 0. I'm going to take 1 and then multiply it by the cofactor of that value, which is the minor at this location. So it's going to be 1 times 1. There you go. And then I'm going to add it to this value, 0, and then block out that row. 0 times the cofactor of that location. It's going to be a negative because it's in the negative spot. It's going to be the negative of the minor. The minor is the determinant of this. The determinant's -4 times 1 minus 0. So we have -4. But then 0 times -4 is 0. You know what I mean? So sorry I went through that whole process. But yeah, plus this times the cofactor. Cofactor is positive in that location. So it's going to be positive of the minor. The minor is the determinant. The determinant is 0. So I'm going to have 0 times 0 on that one. So yeah, the determinant of this is 1. The inverse is going to be 1 divided by the determinant times the cofactor transposed, which is the adjoint. The adjoint is the cofactor of one of the locations, but then transposed. And so if I find the cofactor of this location, the transpose of it's going to be in that location. If I find the cofactor in this location, the transpose of it would be in that location. So we can kind of do this. I know I have 1 divided by 1. That's the determinant. The inverse is the cofactor transposed. Let's do the diagonals first because we so the cofactor of this location is the minor of this location, and there's no sign changes in the diagonal, and the transpose doesn't move it. So we can do those. It's just the minor of this location, which is blocking out that row and column, and finding the determinant of the remainder. So now we're going to do that one in the middle. If I block out this and this, I'm left with the minor of 1. And I'm sorry, we're taking the diagonal, so that's that right there. Apologies. The cofactor of this location is the minor of that location is 1. And then, so now if I take the cofactor of this location, I'm going to put it right there. So I'm going to do that. Cofactor of this location. If there's no sign changes in the diagonal, that's what I'm going to do the diagonals first. And then the determinant 0. Hell yeah. The cofactor of that location, the cofactor transpose goes there. No sign change, so the minor of this is 0. Okay, now I can do, these are going to have a sign change. The cofactor of this location is going to be the minor with a sign change. The minor is -4, sign change is +4. And then it's going to be transposed. So it's going to be right there. So we have +4 right there. Hell yeah. And then, and I feel like I made a mistake in the other one, because obviously if this is -4, the inverse is +4. Yeah, we spent a bit of time trying to do the inverse. We said that if this was E1, the inverse of it was this, was just +4. Yes, so if E1 was our elementary row operation, yeah, so let's go back to this one, because this was the elementary row operation we did, and got our upper. I'm going to take the inverse of this one on both sides. That's going to just make this A. And then I'm going to have inverse of E1 times u. So this has to be L. So L has to be the inverse. The inverse is just this with a sign change. The inverse is the elementary matrix with a sign change. So that's why when you're building your lower, and then over here you have this -4 multiplier, you get +4 there. So we're kind of just showing that, you know, from a proof perspective. Did I lose where the hell we were? Oh yeah, I guess we were on this page. Yeah, so that's why that is a +4 there. And then so the inverse, again, continuing on, I want to find that location, which is the transpose of this location. I mean, I'm sorry. It's the cofactor. When we find the cofactor of this location, the transpose will put it there because it'll cross the diagonal. So the cofactor of this location is going to be 0. It'd be -0, but it's 0. And then the cofactors of these. So I know they're going to be negative, you know, because I'm going to find the cofactor transposed of this location is the cofactor of this. The cofactor of this location gets transposed to that. The cofactor of this location is in a negative spot, so it's going to be the negative of the minor. So I'm going to cross out row, column, and row. And then the minor is 0. So I'm going to have -0 right there. And then this one, last one, cofactor of that location is the minor at that location with the sign change, and then the determinant 0. So there you go. So if this was the elementary row operation, the inverse of it is just a sign change on it. And what we're going to find is if we do an elementary row operation where we change this value, you know, I mean, just because this is the only two we're doing. If I change that value to 2, the inverse of it, so if this is E2, and the inverse of it is not a negative, but it's 1 divided by that value. You know what I mean? So it's the, what do you call that? The inverse? I'm sure there's another name for inverse, but yeah, I think it's inverse. I think there's another name, but anyway, hell yeah. So, and we could prove that one too right now as well. I mean, might as well, because that's what we're doing. We're just kind of playing around with the proofs. So the inverse of this one, using the definition of, is the inverse of this is 1 divided by the determinant. The determinant's going to be the multiplication of the diagonals, or solved other ways, times, you know what I mean? And now we need the adjoint, which is the cofactor transposed. So let's start finding the cofactor of this. We're going to do the diagonals, because they don't change sign, and it's just going to be the minor. So get rid of that. The minor is going to be a star. Hell yeah. The next one is get rid of this and this. The minor is 1. Oh, and that's going to be that location. This location, the minor is star. Hell yeah. Oh, and then now you can see, like once we multiply this through, this becomes 1, this becomes 1, and this becomes 1 divided by that value. So sweet, that's why we get that. But we can continue on. The diagonals is the determinant's going to be 0. The determinant's going to be 0. Like, we're going to do that value right there. Get rid of this and this. Determinant 0. How about this value? The determinant 0. This value. The determinant's 1. Oh, this value will have a 1. Is that right? This value... No. If I cross out those and those, 1 times 0, 0, so that's 0. So they're all zeros. So yeah, we got 0. I'm sure we already did those. I'm sure we did this diagonal. This is probably the last one. I mean, that we haven't done. The transpose would have been right there. But yeah, they're all zeros. So yeah, so there you go. So that's just, I like doing that type of stuff where I don't think people do. I don't think people are like, oh, what's the inverse of an elementary matrix? And it's just like, oh, okay. They just tell you it, and then it just becomes a hocus-pocus thing, just hand-waving. Sweet. So we actually did that one. That was sweet. Okay, so now we can know that if we do an elementary row operation. We already did it. We can classify it as E1. I can instantly take the inverse of it just to have it aside. But because of this definition, I can start to build my identity from this side. Because I can put my identity matrix anywhere, I can put it right there. I can start to build my identity. And the identity matrix is the only one that you can, put on either side of a matrix and do your matrix multiplication, and it still comes out the same. All right, hell yeah. So I think that's the juice. And now what we're going to do is, because I don't have too much more gas in the tank. But I think we're going to do this. I'm going to turn off the camera. Kind of done with this video. I'll put the, but I'm going to try to do this like it was just one setting. I don't know. We can do that later. But, hell yeah. Now, let's just kick this one out. But what we're going to do, anytime that we modify this, we're going to know what the E1 was, and we're going to know what the inverse was. That's why it wouldn't make sense to turn off the camera, because I don't want to explain twice. That would be insanery for me. But hell yeah, so we're almost there. Hell yeah. Alright, so we're going to do some LU factorization, and we have this matrix. Our matrix A is 1, 2, 3, 4, 5, 6, 3, negative 3, 5. Okay, the first thing, this is our matrix A. We want to get our matrix A to be matrix, we're going to try to get it to be a lower. And we're going to do so by multiplying it by something, and that's kind of the, that's called transforming a matrix. This is the transform. We're going to use two elementary operations because this is a 3 by 3. Those are going to be some sort of modification of a identity matrix. And so the one is just multiplying a row. You know what I mean? And so these are zeros. They don't change value. That's multiplying a row by that. That's what we did there. The other one is to multiply. How do I change one of these zeros? I can't just multiply through by anything because those were zeros to begin with. And the only way that I can't multiply this and then add it to that, because we talk about how we can add rows together. And so I'm going to multiply this value times row 1 and then add it to row 2. So that's the other elementary operation. Cool. I'm going to have this be the building of my lower, and then this to be the upper. The first thing that we're going to do is we're going to multiply. We want to change this value to a 0, and we're going to do so. And I can show this. At least do the first one. We're going to. How do you change this value? We're going to use this elementary row operation. We're going to call it E1, and so we're going to do 1, 1, 1, zeros everywhere else. But this is going to be a negative 4. And so a couple ways to look at that. But what we want to do is multiply the top by negative 4. If the top was negative 4, we could add it to this row, and then we'd just be chill. Hell yeah. So that's what we're going to do. So we have 4 plus negative 4. So we multiply the top row by a negative 4. 4 plus negative 4 is 0. This top row will be the same. It won't change. And then I'm going to have 5 times negative 8 is negative 3. And then 6 times negative 12. 6 times... and I should do it like we've been doing the whole video where if this is the elementary row operation and I want to get this value, then I'm going to do second row, third column. Negative 12 plus 6 plus 0. Negative 12 plus 6 is negative 6. Getting a little messy. Okay, hell yeah. So, and then the other rows don't change. 3, negative 3, 5. So that's our first elementary row operation. We're going to set it aside right here. Hell yeah. And we can find the inverse. The inverse of this elementary row operation is going to be 1, 4. So this just changed to a positive 4. By the identity, see, yeah, and this isn't a separate video. By the identity that we've been using, I can start building the lower. The lower is going to be the identity matrix times that, which just is that. So I'm going to have a 1, 1, 1, and a 4, zeros everywhere else. Hell yeah. Now I want to take this new matrix. This is my new matrix. And then I'm going to multiply it by a second elementary row operation. That's going to get rid of that. So that one is going to be, and then be, you know, if and only if this row is 1, you know, is this just going to be a negative 3? Because I'm going to multiply row 1 by negative 3, and then I'm going to take, and then add it to row 2. And that's going to change this row. So I have this as my elementary E2. So E2 is 1, negative 3. Hell yeah, inverse of E2 is 1, 1, 1, negative 3. Hell yeah. And there's 2 more of these that we have to do. And the next one's unique. But if I do this one, if I take this matrix, and we'll try to do it, you know, the top row and column, 1, zeros doesn't change. That shows that doesn't change. The second row is this row, this column. Because this 1 right there identifies this to be 0, and then negative 3, that row doesn't change. So this only changes the third row by a multiple of, you know what I mean? It's going to be, so let's, how do we do this? Actually, no, it spells it out. Negative 3 times this top row plus 0 plus 1 times this bottom row. So we talked about that. So this becomes 0. And then we have negative 6 plus negative 3. So yeah, negative 6 plus negative 3 is negative 9. And then we have negative 9 plus 5. That's negative 4. And I don't want to make mistakes on this. I just want to, you know, just kind of walk through the process. So we're good there. So this was taking A, multiplying it by E1, and then we've taken it and then multiplied it by E2. On that side going that way. Cool, so now we have this. What we want to do, you don't have to do it for this problem, but let's do it. We're going to change this row. I want that to be a 1, but I have to multiply through this entire row by 1 divided by negative 3. I would do this. Like, I have to divide this by negative 3, 1 divided by negative 3, because I'm keeping track of what the reciprocal. What the reciprocal of this is negative 3. Sweet. So my elementary row operation is to take this middle row. So I have 1, 1, 1. This is an identity matrix. The elementary row operation is to change this value. I shouldn't have done that. But we have, so elementary identity matrix, elementary row operation is to do this. So we're going to have a negative 1/3. So that's what we have, a 1 divided by negative 3. I like to do it like this because it just makes it so much more simple to show the inverse is just going to be 1 negative 3. And so that's what we have there. Hell yeah. When we multiply this matrix, that's why I can put, that's why I'm not doing a good, I'm about done, but put this matrix in front and we're going to do row times column. So 1, 0, 0. So that value is 1. This value is 2 times 1, 0, 0, 2. 3 row and then column. You know, this matrix has to be over here to do the row column thing. That's where, you know, doing this is a little bit tricky. But yes, row, column, then this, the second row changes. So we have 1 times 0, 0. So we're going to do row and then column, 0, 0, 0. This one does change. So we have 0 times 2, and then we have negative 3 times 1, 1 divided by negative 3. So that the negatives cancel, and we have 3 divided by 3 is 1. So this becomes 1. And does anything else change? Well, that's just taking this row and then this column. Okay, so how about, yeah, so this value will be this row, third column. So we have 0, and then we have 2. This becomes positive 2. And that's good. And then the bottom row shouldn't change. Zeros, zeros. Cool. So we have 1 and 2 right here. I'm going to circle all the values that are making our upper. Sorry, it's getting messy. But now I'm going to do that same thing. I want to change this value to a 0. I'm going to have my fourth matrix, elementary row operation, starting with an identity. I want to change this value to a, whatever I'm going to put here changes this. And so I'm going to multiply this row by 9 and then add it to this row. That goes away. So this is 9 right there. The inverse of that is going to be 1, 1, 1, negative 9. Hell yeah. And so this is the only value that's going to change. That's going to be in third row, second column. So I'm going to have third row, second column, 0. Wait, what up? Oh yeah, I'm looking at this one, but still, no, yeah. So this value changes. I just need to put this over here. You know what I mean? It would make more sense. We got 1, 0, 0, 0, 0, 0, 9, 1. In this one, I will do 1, 2, 3, 0, 1, 2, 0, negative 9, negative 4. Just because we get so used to, doing these, everything else will be the same. Except this third row. So we're going to get this value right there. So we have 0, 0, 0. So that's 0. This value right there is third row, second column. 0, 9, negative 0 plus 0 plus 9 plus negative 9. That's 0. This value right here, third row, third column. Third row, third column. 0, 18 minus 4. So that's 14. And hell yeah. So ours is a 1, 2 there because we did that extra modification, but we still get that 14. Okay, so hell yeah. And then, so when building the lower, they just say, well, and then based on this equation, we're starting to build the lower. So we got the identity matrix times the inverse of 1. We're going to take this and then multiply it by the inverse of 2. That just puts that right there. Nothing else will change if you do these. And then the E3 is this value. And so the inverse is putting a negative 3 here. Because we multiplied this by a 1 divided by negative 3. I'm sorry, we got to do a... Oh, shouldn't this be... No, it's a negative 3. There's no sign change on this. It's just a reciprocal. Hell yeah. And then the fourth one is this is the inverse. So we have a negative 9 there. And then that's where you can do some hand waving. But as you building your upper, I see a negative 9. Put a negative 9 right there. While I'm building my upper, I had a 4 right here. Put a 4 right there. I had a if I had a 3 right there, this should be a 3 on the lower. See, I messed up. This is negative 3. The inverse is a positive 3. So there's positive 3. So that shows you that even just the hand waving of just being like, hey, I see that, that's got to match. Where it's just like this is overly complex, and it shows that, hey, I made a mistake. And you can make little mistakes. The more work you do, the more mistakes that you're going to make. So, hell yeah. And I do over on the work for sure. All right. And but that kind of shows that as we're building this lower, we're multiplying those matrices together. The last thing I want to do is just show that we could have done those two in that order. So what's E3 times E4? We still have to multiply them in this order where we take E3 and E4. So if I do that, I think we just get... And yeah, let's just walk our way through this. I think it's good. Just taking simple matrices, because I would just say so. If we do this multiplication, it's just going to happen. So let's do the top row. This one is going to be first row, first column, 1, 0, 0. There we go. This one is going to be first row, second column, 0, 0, 0. Hell yeah. This one is going to be first row, third column, 0, 0, 0. Second row is going to be second row, first column, 0, 0, 0. And then this one is going to be second row, second column, 0, negative 1/3, and then 0. And then this one is going to be 0, 0, 0, 0, 0. And then we have, this value is going to be third row, second column, 0, 0, 9. So yeah, so all we did on this one was just pick up those two values. And I bet you these ones you could switch the orders of. No. Why can't you? That would be fast. You're supposed to not be able to switch this order. It has to be E3 times E4. It cannot be E4 times E3. And I really don't even want to prove that. You know, I mean, you go prove that on your own. Like, multiply those in reverse and see why it messes up. That's really fascinating to me. Okay, hell yeah. And then what we would do is we would say, hey, this is, and then we're going to multiply by E2. If I multiply by E2, I'm probably just going to pick up a negative 3 right there. And then when I multiply by E1, I'm just going to pick up a negative 4. And then there you go. There is my inverse. And then all I have to do is take that and multiply it by the identity, which doesn't change, and that builds the lower. So I can wait to build the lower. So that is fascinating. If you're doing upper-lower composition, you can kind of just keep track of what elementary row operations you're doing, but it's just tedious because E1 is going to be a 9 by 9 matrix where this value is going to be negative 4, and then you got to put zeros everywhere else and then have your identity, you know what I mean? And then your inverse, you know, keeping track of that is just going to be 4. But it was fun to walk through the process of finding the inverse as 1 divided by the determinant is just 1, and then finding the adjoint of that matrix. Okay, so does that do it? You know, like, how far did we get on this one? I mean, we should. Well, we did it a little bit different. So, and all we got was an up. No, we got an upper while we built our lower. But our upper and lower is a little bit different. Our lower is 1, 4, 3, negative 3, negative 9, 1. And then our upper is 1, 2, 3, 0, 1, 2, 0, negative 9, 14. Sorry, we already, 0, oh, no, 0, it's an upper. 0, 14. So yes, so we got a slightly different lower and upper because we did one extra elementary step. So their upper was this, ours is a 1 and a 2 right there. Okay, but and then where does that example end? So what they're going to try to do is, and that was it. They were just trying to show what the upper and lower is. They weren't trying to find the inverse. But hell yeah, let's end on a crispy note. So we have matrix A. We know that it's equal to the lower times the upper. And we found our own, you know what I mean, a little bit different. And we should kind of double check that if we do the multiplication of these, I got that first row, and then we got 4. That's 4. 2 times 2, 8. 8 minus 3 is 5. 12 minus 6 is 6. 3. 6 minus 9, negative 3. 9 minus 18 plus 14. Ooh, is it 5? 9 minus 18. 18 plus 14 is negative 4. Not positive 9 minus 4 is 5. Hell yeah. So we're good there. So we have our upper and a lower. So now we're going to do that last part, is the fact that the inverse of A is going to be the inverse. So lower times upper is A. And so it's just the inverse of the lower times upper. Same thing. We're gonna say, hey, if this is something, then we're gonna say, you know, we're gonna say, hey, A times inverse A is the identity. We're just given the fact that we have A inverse. So that's what we're starting with. So therefore, if I multiplied by A, I would get the identity. So that's kind of the tricky part. How do you go from here and start the proof? I'm going to go LU times this. The inverse of LU is the identity. And now I'm going to do that guessing check process. Or we just know from proposition that, well, shouldn't this be inverse U times inverse L in this order? And now the proof begins. Because I can do that, this becomes the identity, basically goes away. Then these two get multiplied, and that becomes the identity. You know what I mean? So just in a few steps, we have that. So that's what we're going to do. We're going to say, and what do we want to find? We want to find the inverse. All right, hell yeah, I want my battery to last on this one. So the inverse is, you know, again, it's that. And then we just prove that this LU inverse is, oh, did I not do it? Yeah, no, right here. But this, yeah. So I just said that, yes, you get to here where, hey, LU times inverse U inverse L. This right here is that. And so, yeah, so inverse A is just this. So inverse A is inverse U inverse L. Now we can do it. But what the hell is the inverse? Oh yeah, I forgot. This one sucks. Because we have to figure these out. Inverse of U is the determinant, 1 divided by 14. We're just going to try to crank. Times the adjoint. Adjoint is the cofactor transform. Let's see how fast I can do this. So I'm going to, diagonals don't change, and this is just the minor. So we have 14. This one is 14. This one is 1. Okay, now this one should go there. 0. This one, this one was 0, 0. Now this one is 4 minus 3 is 1. Hell yeah. And then these are going to be negative. I'm going to put a little negative just because I'm going to try to find the minor of, this one will go there. The minor of this location is 0. The minor of this, oh, see, it went there. So now this one, minor of this location is 28. So it's negative 28. And then this, whatever, like this location is 0, and so that goes right there. This location is 2, and it's going to be negative 2. So I think we got it. The lower determinant is going to be 1, negative 3. And then we have those spots. Diagonals don't change. Negative 3. And then this one will be 1, and then negative 3. So 1, negative 3, 1. No, I did that in the opposite order. This is negative 3, damn it. The middle one is 1. Once I get rid of that row, determinant's 1. And that's right, yep. Okay, diagonals. So, ooh, tricky one. Negative 36. Minus a minus, so plus 9. If it's plus 6, it's negative 30. Plus 3 is negative 27. Negative 27 right there. Transpose it, negative 27. Now this one, 0. And I can figure out the diagonals. So we have 4, that's negative 4, it goes to there, negative 4. This one is 0, 0. This one is negative 9, it goes to 9, and it's going to go right there, 9. This one is 0. Hell yeah. So I think we're pretty decent, and now we need to multiply these together. Ugh. Yeah, it is a lengthy, sucky process, that's for sure. So I'm just going to try to do this as fast as I can do it. And probably use calculator. First row. Yeah, so we got a lot going on. 14 times negative 3 plus negative 28 times negative 4 plus 1 times negative 27. So we get 43. Second row. 14, 0. Negative 28 times, is this 1? It says this, oof, yeah, times 1. Negative 28 times 1 plus 1 times 9. That's negative 19. Still first row, second column. 0, 0, and this is negative 3. Second row, we got, oh, did I do that right? Yep. 0, 14 times negative 4 plus negative 2 times negative 27, negative 2. Alright, second thing, 0, 14 plus 8, minus 18. 14 minus 18, negative 4. Third row, 0, 0, 6. This one, we're getting easy. Hell yeah. Negative 27, 9, and negative 3. And then we have this. This has to be divided by a 14 times negative 3. 14 times negative 3 is negative 42. So we have negative 42, and this is our inverse. We got to double check it. So first row, first column, 1 times 43 plus 2 times negative 2 plus 3 times negative 27 is negative 42. So I'm just going to, I might have made one little error, but this will build the identity. A times inverse A, and this is all inverse A. You got to divide by that determinant. Anyway, and I might have made some little errors on the other columns, but hopefully we didn't. And that shows that we can get, that is the inverse. So that was the process. Find your lower, find your upper, using elementary row operations, using the proofs to build your lower. So now this should totally show you, you can build your lower at any point. And now we know how to build the lower. That was the juice. If my camera cuts out, see you later. But, yeah, where's the, this was the proof. So here's the lower. And yes, you can do it because of associative property. You can do those first, and then add that one, and then add that one, and then multiply it by the identity. But the reason you can you got to start with something, and that's why you start with that identity, and then, that's why you can build it while you're doing the upper. So that hopefully explained that. Holy hell, this was good. And it's good just to do your first rodeo. This was my first rodeo. So hell yeah, thanks for joining me. And yeah, I really don't want to check all these values. We can check one more before my camera cancels. But hell yeah, we'll just check this next one. So we got negative 19 times 1 plus 2 times negative 4 plus 3 times 9. And yeah, so that's going to be 0 because we're shooting for that value. The next one, negative 3 plus 2 times 6 plus 3 times negative 3. That's 0, so we're good there. This middle value, this is going to go on a limb. Might have made some errors, but it's going to be 4 times negative 19 plus 5 times negative 4 plus 6 times 9. Oh, and divide by negative 42 and we get the identity of 1. We'll do this one because it's the diagonals that are, well, I don't know. They're all important. You can't mess up anything, but hell yeah. So we got 3 times negative